let's see this one. So we have calculate delta G in kilojoules for the reaction below when you have your various concentrations and you're given the reaction 3x plus 2yz goes to 2xy plus xz2. Do you know what you would need for this?
Yeah, it's the delta G equals G naught plus RT on P.
Perfect. Do you know how we would set up Q?
Yeah, that's in like the products of
Mhm.
the
Perfect.
reactants, and then square plus Q. RT is that 0.081. Is it?
Yes. Yep. Perfect. Right. So R here is 8.314 joules over mole Kelvin. So we're going to change that to kilojoules. So that's 0.008314. Perfect. The let me do it real quick. Sorry.
I think it is Q. I just like plugged it all straight in.
Yep. So it should be xy squared is 0.3 times. Got Q 857.6. Okay. So unless we both did it wrong the same way, I think that's Q. So then delta G should be negative 5.7 kilojoules per mole plus this, and then temperature is already where it needs to be, and then ln of 857.6. Yeah, so I got delta G equal to 22.5 kilojoules. That's a lot. This has to be plus. This is negative 5.7 plus 22.46. So then plus. I didn't finish my question. So delta G is 16.8. Is that what you got? Cool. Okay, so that's one of them. And then you know how you would solve like to get rid of the ln if you needed to solve for Q. Yep. So you could always check your answer once you have this by solving for Q or a different variable in your question, and see if you get back to like the original values and stuff. So that's always like if you have extra time on your exam, something that you can do. Okay. Okay, so that one I think you feel comfortable with.
Yeah, it's not. It's like if I'm given an equation, I can kind of figure it out.
Yep.
I think it was the concepts.
The concepts, okay, because I'll look through that a little bit and see if there's.
This is the general.
Okay, so if we had like. Okay, so if we have these three KSPs, or sorry, these four KSPs, which one would produce the most carbonate ions?
With the CSC,
Why did you say that one?
has a biggest dissociation.
Perfect, right? So this has the highest KSP, which means most soluble. Right, so then which one would have the fewest ions in solution?
But I'm sorry.
Perfect, so this would have fewest ions in solution. Okay, so that's just when they're all 1 to 1 to 1. So if we did have something where it was like, no, and something like this, so we have silver carbonate. Now, when we do this, it's still only producing, say this is also 2. Right, there's still only producing how many ions of the carbonate?
One,
1. So how would this compare to the calcium carbonate?
would it be less? You know, it'd be the same.
We would probably need to solve for it, right? So if we looked at this, we're given KSP, we could write out both equations. We would have calcium carbonate. And then we would have the silver. Right, so if we were just to write up an ice table, you would see that the concentration of the carbonate is not going to be different between the two of them, right? Overall ions in solution, we would have more silver ions compared to calcium ions because we're going to have 2 moles for every 1 mole of the anion that gets produced. But if we were to write out an ice table, right, we start off with 0, so this is going to be plus X and plus X. So in solution, we would have X and X, so KSP would be equal to X squared for the calcium carbonate. However, if we did this silver, then it would be plus 2X this time and X. So equilibrium is 2X and X. So now KSP becomes 4X cubed. So it would look like the equilibriums are going to be the same because they're both X. But X will be different, right? When we solve for
equilibrium concentrations will be different.
Mm-hmm.
Okay.
Yep. So it might look similar because they're both just X, but it is going to be different. So if we did 2.5 times 10 to the negative 4 equal to x squared. What does x become here?
Can it be the number of ions in the solution, or is it just the rate of dissociation?
It is, it's related to the number of ions in solution because it's only telling you about the soluble ions. So it's the concentration of those ions in solution is what it's really telling you. Right, and it's telling you, right, KSP stands for the equilibrium of the solubility product. What is solubility? What is solubility? Concentration, number of ions in solution. Product, multiplication, you're multiplying them together, right? So it breaks down this concept of the ions in solution. Okay, so x here becomes 1.6 times 10 to the negative 2, right? But then if we did this one here, now x becomes 3.96 times 10 to the negative 2, or 4.0 times 10 to the negative 2. So which one has more ions in solution?
Silver.
The silver produces more of that carbonate ion.
Yeah.
Does that make sense? Like how we solved it and found that?
Yeah.
Okay. It's hard to tell just based off of looking at the formulas, which is why you have to do the full math. Because this is one where you double dip, so it might not like look directly as it seems when you're doing it. But it's telling you, right, the concentration of ions in solution. So that'll tell you what the concentration of that ion is. Okay, does that make sense concept wise?
Like I feel like in my mind, it would be backwards, like that the calcium carbonate should have more ions, like the math.
Yeah, it does seem backwards, and I understand where you're coming from with that. But we have to remember that it's multiplication of very small numbers. So that math is what gets funky. And in order to make that number high enough, right, that silver is double dipping. So that's going to throw off the math and everything else. That's going to throw off our carbonate ion there. So I think if you back it up, especially if you're a formula person, right, back it up with your numbers, and that'll help you with concepts as well. Did you have any specific questions? Okay, we were just kind of going through the quiz, just concept wise and talking about it. I don't think I'm supposed to totally direct, like I'm changing up some of the questions so that it's not directly it, but concept wise, just kind of going through there. So if you have anything that pops up, just let me know. Okay, any other questions on that? And then you could do the same thing for, I guess like aluminum. Right, if we had this salt now this becomes even more complicated. So if this breaks up, we now have, now this breaks up into 2 aluminum 3+ and 3 CO3 2-. So now this gets even funkier, right? If we do the ice table, where this is 0, this is plus 2x, this is plus 3x. Now this becomes 2x and 3x. So now KSP is 2x squared times 3x cubed. $27, right? Yeah, 27x cubed. So now this is 108 x to the fifth, right? So now you can see x is going to be very different here in comparison to the other ones. Right, so this x is now, if we assumed that KSP was the 2.5 still, KSP is now 7.5 times 10 to negative 2. Right, so that's a completely different solubility in comparison. Okay. So when in doubt, I would say just draw a nice table. Usually you can get to the correct answer if you have that. All right. Okay, let's try this one. So if you have something where okay, so we have, will this form a precipitate? And we're given 20 mils of calcium nitrate and 7.5 mils of lithium fluoride. And we're given that the KSP of calcium fluoride is that number. Okay, so how are we going to set this one up? Kind of, but you could get away with not doing a nice table with this one.
This one I can.
Don't know. Okay. Okay. So what we're given is calcium nitrate and lithium fluoride, but we're asked for calcium fluoride. So is calcium fluoride given to us? No, right? We don't really know where that's coming from. So whenever you see something where they're mixed together, I want you to think of like you have two beakers and you're going to pour them into each other. Okay, so this is going to be a double displacement reaction whenever you see that word mixed. So you can set up your chemical reaction first. So you're given calcium nitrate and you're given lithium fluoride, right? You want to write out the chemistry that's happening. We know that they have concentrations of these, and if we're given concentrations, we know that these are aqueous. And we'll be able to check that from our solubility chart as well. And if we're going to predict the products, what do we do to our reactants?
Sorry, can you say that again?
If we're going to predict our products, what do we do to our reactants?
Wait, think right a balanced equation. Are you asking like what they are? Oh, sorry. Like the ally and then three.
Right, so we know that calcium, since calcium fluoride was given to us, we know that that's going to be one of our products, but we need to see where it came from, right? And what it's coming from is the calcium nitrate being mixed with the lithium fluoride. We need to write and make sure that our equation is balanced. So how are we going to do that? Perfect. And then do we know what lithium nitrate is in terms of solubility or phase? Right. Yep. So this is going to be aqueous. Anything with group 1 and anything with the nitrate are always going to be soluble. And what do we know about calcium fluoride? Yep. Perfect. Yep. So whenever you're given a KSP for something, you know that it will be a solid. It can't have a KSP unless it's a solid. Right. So what this breaks down into is those net ionic equations that you talked about probably at the end of last semester. Right, if we were to break this up into all of your ions, we would see that the lithium and the nitrates don't matter to us. And what we would be left with is calcium plus and two fluoride ions forming calcium fluoride. Is this the way that you write a KSP equation? Is this the way you write a KSP equation? How do we usually, right? If I gave you a solid and I said, write the solubility product, what is? Yep. So you wouldn't put the solid, right? So we can call this equilibrium too. This is actually equilibrium both ways. So we're not going to put the solid in our KSP. And where usually is the solid if we were to write the KSP and include it? Is it on the left or the right? It's usually on the left, right? We say, okay, we have this solid, calcium fluoride, and it's usually a solid, but now we're saying it's going to break apart into some ions, calcium plus and 2F minus, right? So this is what the KSP is equal to. Correct, right? So if we write it this way, our solid no longer gets into our equilibrium constant, and so we don't have a numerator, we just have a 1. What does K look like if we were to write the equation above it? K this time is 1 over calcium 2 plus times F minus squared.
So the KSP is for the bottom reaction where we flipped it?
Yes. Yep.
Okay.
You can solve for that purple K. It's just the inverse of your KSP.
And we know the KSP given is for the flipped reaction
because that's convention, right? That's how you write it. It's not KSP unless the solid is on the left forming its ions. Right, you'll always, if you're given KSP for something, always put your solid on the left.
and then we get the concentration. We have to combine the volume.
We do, right? So all of this is just set up, and we haven't really started answering our question yet, right? So in order to find if the precipitate forms, we need to take into account the volumes and the concentrations of both of our reactants that were given. Because what can we find out from the concentrations and volumes? Yep. Yep, we can find the amount of solution. What unit of amount are we finding? It's moles. Yep, because if we were to take calcium nitrate, we're given 4.5 times 10 to the negative 2 molar. Remember that molar is moles over liter. So if we want to get to moles of calcium nitrate, we have to multiply by what? We have to times 0.02 liters. We do have to change it this time. Right, so that would be saying that we have 9.0 times 10 to the negative 4 moles of calcium ions. Yep, so then to get to concentration of calcium ions, we're going to take this and divide it by our total volume, which is 20 plus 7.5, because we're going to put them into one beaker. So we'll have 0.0275 liters. And so you get 3.27 times 10 to the negative 2. Molar calcium ions. And then what do we do for fluorine? Yes, yep. So this time we have to multiply it by 2, because if we were to break this apart, right, this becomes calcium 2 plus and 2NO3 minus. But if we're going to do the same thing for lithium fluoride, this breaks apart into lithium plus and fluoride minus, but in our reaction, we have 2 of these. So that's 2 lithium and 2 fluorines. So we'll take 7.5 and 2.2, so. Get 0.00, oh. -4 fluorine, and then times 2 is 3.3. And then how we get to concentration there. Perfect. So same thing, 0.0275 liters. And we end up with 1.2 times 10 to the negative 2 molar fluorine ions. I don't think we do, now that I'm thinking about this. I don't think we need to take that into consideration for the 2 now. Because we're only given this for lithium fluoride. So right, if we're just gonna take the concentration of like, right, we have 2 beakers, this one has lithium fluoride, we're just taking the number of moles in that beaker into consideration, right? So we need to know how much we're starting with and not necessarily like how much we would need for both of them. Or how much we would need to completely react in that sense. Right, so just take this into account as if it's standing alone. You need to find how many moles of fluorine you have. So you don't need to multiply, you don't have to multiply it by 2. That's going to screw you up later on. We'll take the 2 into account when we start solving for KSP. So you don't need 2 here. This is just lithium and fluorine. So we have 1.65 times 10 to the negative 4, and this will divide by 0.0275. So you get 6.0 times 10 to negative 3 molar fluorine. Because we're not, even though it requires 2 for the reaction, we're not gaining 2 by mixing them. We only have how much we started with, and how much we started with is based off of the singular lithium fluoride that were given to us in that solution. Okay. So how this now plays into KSP is that if we were to write the KSP, right, we said that was calcium fluoride. Is forming calcium and 2F minus. Our initial for our ice table, right, is now what we solved for our molar concentrations here. Right, because that's what we're starting with. We're mixing them before a reaction even happens. That is what we have in solution. So we have 3.27 times 10 to the negative 2, and we have 6.0 times 10 to the negative 3. So what is that initial? What can we solve there? What letter can we solve for during initials? We can solve for equilibrium. But is that going to be K or is that going to be Q? Q, right? We don't know if these concentrations are going to tell us if we have, right, enough ions in solution, right? So we need to compare Q to K to see, okay, is a precipitate forming or is a precipitate not forming?
And if a precipitate forms, does that mean it's not equilibrium?
So if a precipitate forms, that means that we are past equilibrium. Okay, and I can.
Would you want it to be less or like greater than this?
So you tell me. If we have.
I think it's greater than the speed of the precipitate is forming because of the
So if Q is less than K, which way do we go? Left or right in our reaction? To the products, right? So if Q is less than K, we're forming products. So if we have to form products, are we forming more ions or are we forming more solid? We're forming more ions. So if Q is less than K here, then no precipitate is going to form. But if we have Q greater than K, which way do we go? We go towards the reactant. So if Q is less than K, or sorry, Q is greater than K, we go towards the reactants, and does that produce more solid or more ions? More solid. So if Q is greater than K, then we have a precipitate. Does that make sense? Mm-hmm. And that's why we need to look at the way that the equation is set up to make sure that we're using the correct Q, or we're using the correct K when we're comparing Q versus K. Okay, so how are we going to solve for Q? You don't need to do the full ice table. Nope.
Concentration of CA and F squared.
Perfect. Right, so here is where the squaring and that 2 comes into play, right? We're not double dipping here because we can't create more ions. It's just what we're given, but we do need to square it in this case here so that we find the correct Q value. I got Q is equal to 1.17 times 10 to the negative 6. Is that what someone else got as well? Okay. So I said that Q is 1.17 times 10 to the negative 6, and KSP was 3.5 times 10 to the negative 8.
So it is fine.
Yep. So in this case, Q is greater than K. So we have to go towards reactants, which in this case is your solid. So a precipitate forms. Okay, and if we looked at this, if we just solved Q versus K here, and we only wrote out, right, our calcium plus and 2F minus going to calcium fluoride solid, right? If we wrote it like this, but we still know that we need to solve for Q versus K, right? We might think that Q is greater than K and say that no precipitate forms because we were going towards reactants. But we need to remember that KSP is always going to be solid breaking apart into ions. So we need to compare to the correct chemical reaction that's happening. And so in this case, Q is less than K is not for this one, but for calcium fluoride splitting apart into the calcium 2 plus and 2F minus ions. Do you see the difference there and why that's important? Does that help with that type of question?
Yeah.
Yeah.
I think I saw that on Twizzlers. I don't know.
Yeah. Yep. So, and the big thing to remember is that you can always solve for moles of something given a concentration and given a volume, right? V and M, we remember M1 V1 is equal to M2 V2. And this is telling you that the moles at the start is equal to the moles at the end. It's just being diluted at some point. And that's just what we're doing. We're just adding solution to something like that. Okay. Any other questions there? Okay, so then in similar fashion, right, let's say we had calcium iodide. And we said that KSP is equal to okay. Now we can see what happens to a solid in solution, right? So we know that if we have calcium iodide, this is going to switch from calcium 2 plus to 2I minus. Okay, and then we can use Le Chatelier's principle to see if precipitate will form, if more solid, or if more ions will form, or if nothing happens. Okay, so one of the big things that we can do is that we could add water to our solution. What happens if we're adding water? Do we form more precipitate? Do we form more ions, or does nothing happen? So let's see, more ions, solid, nothing. And you said more ions. And why does that happen?
The KSP is based on concentration.
Yep. So, right, we know that at equilibrium, we have a certain concentration. We can solve for that. Right, we would be able to solve for the solubility of either one of these. This one is a 4x cubed one. So, right, whatever, even if we say that x is equal to 5, right, that's per, let's say, 1 liter. If we were to make this 2 liters, we still have that same number of moles of those ions in solution, but now instead of 5/1, now this becomes 5/2, so our concentration goes down to 2.5 molar. That now changes what Q is. If Q's values are going down, Q becomes less than K, so we have to form more ions in solution. So adding water dilutes your solution, dilutes the concentration, and therefore causes you to have more salt become soluble in solution to make up for the fact that ions were lost, right? Concentration was lost when you added more water to the solution. Does that make sense why that's happening there? Okay, what if we added calcium chloride? Do we have more ions? More solid? Or nothing? And why do you say that?
Plus goes up.
Mhm.
And the first-
Perfect. Yep. So if we have more calcium chloride in solution is going to break apart into calcium 2 plus and 2Cl minus. The 2Cl minus doesn't have anything in common with the calcium iodide, but we have now this calcium 2 plus already hanging out in solution or contributing to the ions in solution. So that concentration is going to matter to the Q value. That's going to increase the value of that concentration of calcium, causing Q to become greater than K. And so we need to form more reactants. So more solid is going to form. So what does that mean for the concentration of the chloride or the iodine ions?
It goes down.
It's going to decrease, right? So the calcium, you probably add enough where it's not going to make a difference to the calcium concentration, but your iodine concentration is going to significantly decrease. So if you were to write an ice table, the plus X, or bless you, the minus X in the calcium you can neglect, but the minus X in the iodine you could not neglect. Okay. And then same thing, if like iodine ions were added, it would do the same to Q. That would increase and then move it that way. But if you just added like sodium chloride, there's no common ion between sodium chloride and the calcium iodide. So this would have no effect on equilibrium. And so nothing would happen there.
Added more. Would that just increase? Dissolve. Iron.
If you added like more solid calcium iodide, I think that would cause more. I think, how would that happen? Let me think. We have calcium iodide that has calcium 2 plus and 2I minus, and this has a concentration. then you add more solid, I don't think it would do anything if you're adding straight solid.
The KSP has to be the same.
Yep, this KSP has to be the same. It's already at its equilibrium. So no more ions are going to go out into solution and no ions are going to form back into solid because it's already like saturated, right? It's already saturated with the KSP. It's already at equilibrium. And since the solid does not contribute to the K value, adding as much solid as you want does nothing to the system. Think of it as when we're doing like partial pressures and you add an inert gas, right? It does nothing because it's just adding it all the same to partial pressures with that gas. Adding a straight solid is not going to do anything because it doesn't contribute to the K value. Good question. But if you added calcium ions and iodine ions, then that would form more precipitate because those are direct ions that contribute to the KSP. Great. Anything else? How do we feel about acids and bases so far? Okay. Okay. Anything confusing about them? Okay. I think the big thing to note for y'all is just the difference between right, if you have an HA minus, we'll call it, right, plus a proton is going to be H2A, right? If we're adding a proton, this would be the conjugate acid. I'm sorry. Plus a proton is the yeah, conjugate acid. Because if this were, let's say, HNO3 minus, make it H2SO. I am messing all of this up. This one. Right, plus is going to be H2SO4, and that's like your strong acid. But if you subtracted an ion or subtracted an H, this becomes A minus. This is going to be your conjugate base. And this would be SO4 2 minus that way. Right, so you can go either way. Plus an H or minus an H is going to be the big thing here. If you're ever confused, my biggest piece of advice for determining conjugate acid, conjugate base is just to take, right, HCl. You know HCl is a strong acid. So its conjugate base is going to be Cl minus. And that is minus an H ion. So then you can look at it that way and then look at your whole chemical equation to see what's happening there. I think sometimes that just gets confusing for students moving forward that way.
So when you talked about in class today, it was like, you know, you go from like the concentration of like hydronium and to pH, pOH, and then you can go to concentration of the hydroxide.
Yep.
And you go straight from the concentration of like the H3O to the concentration of OH, or do you have to go through like those steps?
There is a way to do that. I don't think she's introduced that to you yet. K,
Something about it class and then she didn't do it.
yeah. So KW is the dissociation of water, which is H3O plus and OH minus, right? And that's if right? Where water is acting as both an acid and a base. So you can get the Kw of water, which is H3O plus and OH minus. So if you have the concentration of H3O plus, you can use the Kw in order to get to the concentration of OH minus.
And is KW a constant?
Kw is a constant, but it's a constant for specific temperatures. So at, I think it's 25 degrees Celsius, it's 1.0 times 10 to the negative 14, but it does change depending on the temperature that you're at. So if your reaction is at 25, then you can use this, and you can always check it this way, right? You could do the long way and then check it by this, or do it the shortcut way and then check it the long way if you have more time. Yeah, but that's the shortcut. I think that's it. Have you started talking about buffers yet? Okay, that'll be fun once you do that. That'll probably be Friday. Buffers is when it gets all complicated. All right. Anything else for today, y'all? Okay, cool. We'll stop there, and then if you have anything else in the meantime, just let me know. Thanks for coming. Hoping that was slightly helpful. I think next week there'll be more attendance.
Okay.
This, I think, is my favorite part of general chemistry coming up, so hopefully you enjoy it. Yeah, thank you.